So my talk today will be about cold atom physics. Yeah. So about like 15 years ago, Professor Yang encouraged me to join this field of cold atom physics. And I think the most important thing I learned from him is it's very lucky for young people to grow up with a growing field. So I think in the past 15 years, this field has been expanded a lot since it started in now 20 years ago, from 1995, when the first Bose-Einstein condensate was realized with alkaline atoms. Now I think we fully enjoy research in this fast expanding field. Now just to give you some very brief idea about what cold atom is. So we have these very low density atoms which are trapped in a it's this very low density atoms which are trapped in this high in this vacuum, and the temperature is also very low in order to reach the quantum degeneracy of these gases, but the system is very clean and you can control the interaction between the particles. Okay, now today you may have noticed that there are three keywords in my title, which is the gauge field and the Li-Huang-Yang correction and off-diagonal non-range order. And this is three very important contributions from Professor Yang, which nowadays also have very strong influence on the physics of cold atoms. Of course, there is another one, which is a solution to one-dimensional system, and that Xiwen and several others have talked about in the morning. So I won't discuss this in my talk, but I mainly focus on the three of them. So let me begin by briefly discuss what are they. Now, you may have known that the gauge field is a concept of the charged particle, right? But now the cold atoms are neutral. So how are they going to have the gauge field? Now, the idea to realize a gauge field for neutral atoms is like this. The very simple principle, basically, if you have a magnetic field texture in the space, now if the atom traveling around the space and the spin is locally polarized to the direction of magnetic field. Now, if the particle travels around a closed loop, it will pick up a Berry phase, which is basically the solid angle expanded by the spin vector. And we know that this Berry phase acts as a gauge field to the particles. So in this way, we can realize the abelian gauge field, whose effect is like a synthetic magnetic flux. And we can also realize the non-abelian gauge field, like the idea by Wilczek and Zere, which generalizes the concept of Berry phase to the non-abelian case. And you can realize the effects such as spin-orbit coupling for cold atoms. Now, this direction have lots of exciting developments in the past few years. For example, with this synthetic magnetic field, one can create vortices in a condensate. And you can observe the critical magnetic field for the vortices to enter a superfluid. And also, we can put the gauge field with lattice. And in this case, we can have the topological band with a non-trivial Chen number. And this Chen number has also been really measured experimentally. Now, we also can realize the non-abelian gauge field whose effects is like spin-orbit coupling. You can have the spin momentum locking under the modified band structure. Okay, now this is the first thing I talk about is gauge field. Now let me come to the second keyword, which is the so-called Li-Huang-Yang correction. Okay? Now what it is, I think back to the 1950s, Professor Yang and his collaborators start to think about the problem of what's the role of interactions in a Bose-Einstein condensation transition. Now, so they pick up a simple model, which is the dilute gases. But then immediately they realized if you just take the delta interaction, contact interaction, the energy will diverge once you go beyond the mean field level. So they take the Fermi pseudo potential, which is now known as Huang-Yang pseudo potential in the content cold atoms, and this pseudo potential will eliminate all the physical divergence in a zero range model. And with that, they come to a correction to the energy beyond the order of the mean field. And the physical meaning of this correction is like this. Suppose I have a condensate where particles all condensed in a zero momentum state. But after you turn on interaction, some particle will be excited to the final momentum state by this collision. Okay? Now this will give you a Bogoliubov type of linearized phonon mode at low energy. Now if you count all the 0-point energy of these phonons, it will actually diverge. Okay? Now, but this divergence can be eliminated by the Huang-Yang pseudopotential I just mentioned. So this will give you a regular correction, which is now known as the Li-Huang-Yang correction. So in another word, Li-Huang-Yang correction basically takes into account the fluctuation energy of the low energy modes. Okay. Now this correction is small if the interaction is small, but once you turn on the strong interactions, that can be observed. Now in cold atoms, there are a number of experiments that have been observed these effects. For example, from frequency shift of collective modes, from density profile in high harmonic trap, also from the pressure measurement of the equation of states, and from the so-called contact measurement of the momentum distribution. So all these effects, all these measurements are consistent with the prediction by Li-Huang-Yang back to half century ago. Okay, now come to the third keyword, off-diagonal long-range order. Now this has been introduced by Professor Fisher this morning. So basically the idea is also how to characterize a Bose condensate with interaction. And the idea is to introduce this off-diagonal correlation function. And when you have the Bose condensate, this one is not zero, even R and R prime are far separated. Now this paper is now well known, okay? But there is one concept which are not widely discussed in literature. And I put here, this is the first paragraph of Professor Yang's Review Modern Physics paper. Now he said, okay, now the existence of diagonal long-range order in Rho n will imply its existence in a reduced density matrix in Rho m if m is larger than n. That means if I have ODLRO in one body density matrix, I will automatically have the long-range order in two body and three body density matrix. Okay? So then he says the smallest n for which the off-diagonal long-range order occurs gives the connection of m particle that in a sense form a basic group. Okay? So he introduces the concept of basic group that is the smallest group density matrix which have off-diagonal long-range order. Okay? Once you have density long-range order in n, then you will have automatically have that in the high order. Okay, now let me ask a question. Okay? Now, do we have a situation like this? We have superfluid where we have the off-diagonal long-range order in a two-body density matrix, but not a one-body density matrix. Okay? Or can we have the trion superfluid? Namely, it have in the three-body density matrix, but not two and not one. Okay? So in other words, do we have superfluid bosons, not fermions, okay? With basic group 2 or basic group 3? Okay? That's the question I want to ask. Okay, now I want to tell you it is this question, okay, that brings the connection between these three concepts very nicely. Okay? Now how this works? So this problem will go to the Bose-Einstein condensate with single particle ground state degeneracy. Okay, now let's go back to the original concept of Bose condensate. So basically there, you will have, if you have a p-square momentum distribution, okay, there is a unique single particle ground state at zero momentum. Then the boson will all condense there, right? So if you have boson condensed in a zero momentum, now the interaction, all it can do is just play some quantitative effects. That is some correction at high energy, high order. Okay? Now, if you have another situation, for example, if you turn on like a spin-orbit coupling, then the single particle ground state has degeneracy. It's not at zero momentum anymore. Okay? Now, if you have degeneracy, the question is, what boson will condense, right? It will have some frustration. So like an example, like if a human have lots of choice or opportunities, you'll be frustrated, don't know what to choose. Now this is the same situation. Now, if a boson have a degenerate single particle ground state, then it needs to make a choice to choose what state it will condense into. And then in that case, the interaction will play a qualitative role instead of quantitative role. Now, at the mean field level, the phase diagram for the condensate with spin-orbit coupling was worked out by one of our paper back to like 5 years ago. Now, basically, we found that there are two different phases. Okay, depending on interaction, the condensate can either condense in one of the minimum, which breaks the rotation symmetry of the Rashba spin-orbit coupling, or it can condense into a superposition of a pair of different momentum states. Now, since these two states have different opposite momentum, okay, so then once the boson condensed in such a state, it will have the interference pattern in the wave function. Okay, so that this will have automatically have the density modulation along the direction of its condensation momentum. Okay, so in this case, the boson condensation will form the stripe order. Okay, it's not only break the spatial U1 symmetry, but also break the translation symmetry. Okay, so this is kind of a liquid crystal type of states in thermal symmetry. Okay, now then let's address the issue of what's the low energy excitation of this kind of strange condensate, right? Now, suppose you have a condensate along x direction. Now, there will be two low energy modes. Now, one of the modes is a normal superfluid phonon mode, which causes a Bogoliubov phonon dispersion. Now, but there is another mode, which is the relative phase between the two superposition. And this phase basically controls the stripe density shift in the space. Okay? So this is another phonon mode. So if you want to construct a low energy theory to describe the low energy physics of this superfluid, then you need to describe in terms of these two quantities. And also, there are three different types of topological defects corresponding to each of them. Okay. Now, I will not go into the details, but just to tell the results. If we work out the low energy theory for this kind of superfluid, now the theta part is still a conventional XY model, but the U part, which is the relative phase, will have a different kind of behavior. Suppose the condensate is along X direction, then along Y direction, this derivative is a high order one. Okay? It's not normal XY model. So that's because if I have some fluctuation along the Y direction, this just corresponds to a global rotation of the stripe direction, okay, which will not cost energy at the leading order. Okay. And the consequence of this is we know for a normal XY model, the vortex energy is logarithmic depending on system size, and therefore in 2D, you will have a finite KT transition temperature. Now, if you have this kind of low energy theory, that means the energy of the dislocation associated with the U field is not logarithmic depending on system size. Okay? And therefore, it cannot compete with an entropy at any finite temperature. Okay? That means once you turn on finite temperature, okay, this U field will become disordered by proliferating a lot of dislocation in the stripe order. And this will immediately lead to the conclusion that once this U field is not ordered, then you will not have the long-range order for at a single particle level. Okay. Now, but if you consider the two-particle order, notice that here you have a U, and here you have a minus U. Okay. Once you consider U time phi times phi, it can still be ordered. Okay. So this gives us a situation where once this U field is disordered, the single particle Bose-Einstein condensate disappeared, but the pair condensate will still exist until the theta field is disordered at high temperature. It's a normal Bose-Einstein, normal KT transition temperature. Okay, now this leads to a conclusion of a phase diagram for this kind. Okay, so there will be a large temperature regime where you have this charge 2e limmatic superfluid, means that the basic group for the superfluid is 2 instead of 1. Okay. Yeah, this is still theory. Yes, I hope in the future it can be experiments on this. Yeah. Okay, just to mention that there are lots of progress in the field of this by looking at spin orbit coupled quantum gases. I don't have time to go into detail, but you can look at this into my recent review article if you are interested in the developments along this line. How many time I have? Okay, good. Okay, I have given you the first example where we have the superfluid with the basic group 2. Okay, now I give you a second example with superfluid with the basic group 3. Okay, now the example is now in the Berkeley group, they have realized this kind of Kagome lattice, okay, by interference two sets of laser beams. Okay. Now the unique thing of this Kagome lattice is there is a band which is completely flat. Okay. There is no dispersion at all. Okay. I don't explain the detail why it works, but there is a physical reason for this. Now, but this band is at the top of the dispersion, right? So it won't have any effects on the Bose-Einstein condensate. But there is a trick, okay? Now I want to go into detail how the trick works, but it's basically using the idea of synthetic gauge field. Again, okay, you can insert a pi flux in each of the triangle. Okay? By doing this, you basically change the t from minus t to plus t. Okay? And this, by changing the sign of t, you turn all the dispersion upside down, right? So now the flat band will turn from the very top to the very bottom. Okay. Now you will have a situation. Now boson will see a lot of degenerate states at single particle level. Okay. Now how this will work out then? Okay. Now the first thing we notice that if you add the interaction, okay, even at the mean field level to the states, it will already lift the single particle degeneracy flat band because different states, they have different interaction, mean field interaction energy. Okay. However, there are still two degenerate states, which are the condensation at the gamma point and the condensation at the K point. Okay. Now, these two states correspond to these two kind of configuration. These two configurations have two features. First, the density is all uniform. Okay. This minimizes the interaction energy. Now the second is, for each triangle, the phase of the wave function will be either 1 or EI 2 pi over 3 or 4 pi over 3. Okay. So each triangle, the three sides will have its three different phases. Okay. So I call this three color configurations. So once the phase of this wave function satisfies the three color constraint, you can show that it also minimizes the kinetic energy. Okay. So therefore, you have a lot of configuration again. Once their phase satisfies this three color constraint and the density is uniform, okay, both the kinetic energy and the interaction energy are satisfied. Okay. Now that means they still have lots of degeneracy at the mean field level. Okay. Now what we are going to do? Okay. Now we are going to look at the excitations. Okay. So we are going to look at the excitation on top of different kinds of condensate. And you will find here, for the condensate at the gamma point, the Bogoliubov phonon mode have a larger velocity. And here, it has a smaller velocity. Okay, okay, now I need to remind you what I talked about at the beginning about this Li-Huang-Yang correction. Okay. The Li-Huang-Yang correction is basically the interaction energy coming from the 0 point energy of the phonon mode, right? So that means if I have a larger velocity of the phonon, I will have more 0 point energy. And if I have a soft dispersion of the phonon mode, then I will have smaller energy from the fluctuation, from 0 point energy. So that means if I consider my interaction energy beyond the mean field to the order of Li-Huang-Yang level, i.e., I consider this 0 point energy of the Bogoliubov phonon mode, I can further distinguish these two states, which energy is lower. Okay? And in this case, the energy of this guy is actually lower. Okay? So that's what I'm saying. In this case, this Li-Huang-Yang correction not only just the quantitative things, it's play a qualitative role. Right? Okay, but another pointer is if I compute this fluctuation energy, okay, and I find that the fluctuation energy can indeed distinguish the states, but this energy, which I call J, actually is much smaller than hopping energy T. Okay, the maximum energy of this J is 3 orders of magnitude smaller than T. That you can kind of understand this because this is, after all, energy from fluctuations. Okay, now therefore I can have a situation where if the temperature is much larger than J, but much smaller than T. Okay, so that means all this configuration will be thermally mixed. However, the total phase is still in a coherent regime. Okay, now if you mix all these phases, that means the phase can be randomly chosen between 1, 2 pi over 3, or 4 pi over 3. Then the single particle correlation function will be 0. Okay. But remember, it's either 1, 2 pi over 3, 4 pi over 3, right? So if I 3 times the correlation function, then it's always be 1. Right? So that means, okay, if I consider the correlation function of b dagger 3 to bj 3, okay, this correlation function will always be a constant, even I mix all these configurations. Okay. So this comes to the phase diagram where I will have so-called trion superfluid at a finite temperature. Right? And now the question is how I'm going to detect them. So in this phase, the single particle correlation function is already disappear, but the 3-body correlation function will still exist. Now to make some experimental connection with this phenomena, we predict the time of fly imaging, okay, which is a measurement of the momentum distribution for all 3 phases. And you can obviously see they are different. Okay. And then you can also look at the noise correlation in this momentum distribution. It also have very distinct signal. So all these measurements are very standard, very easy detection measurements for cold atom system. Okay. So this will be a prediction for the Berkeley group. They are working on this. Berkeley group. Berkeley. Yeah. Okay. Conclusion. Okay. So the conclusion of my talk is I think the question of asking whether you have the boson superfluid with the basic group larger than 1 will be nicely and coherently make these 3 concepts from Professor Yang coherently together a story, which is the gauge field introduced fluctuations. Okay. And therefore, the interaction and the Li Huang-Yang correction will play a qualitative role. Okay. And then the exotic superfluid with basic group equal to 2 or 3 can exist. And I give you 2 examples. One is boson with Rashba spin orbit coupling. Another is boson in Kagami lattice. There are also other examples discussed in like high jet phase in high TT superconductor, FFL superfluid, or spin 1 bosons. This is some related work in other contents. With this, I thank you for your attention. Okay, now this one I think is really ready to be observed in the Berkeley group, but they should they need to overcome some technical challenge in the inserting pi flux. But this has been done by other groups, so they just need to know how to do this in their setting. Now for this one, the challenging part is how to real Rashba spin orbit coupling. Now so far, I think your colleague Jens Bielmann in NIST has realized one-dimensional spin orbit coupling very nicely. This has generated a lot of activity. But how to generate the Yang scheme to get a 2-dimensional Rashba spin orbit coupling is still a challenging problem for the community now.